And we are live. Today is January 28th, 2024, and I'm bringing Ethereum updates. So we have three main topics today. The first is an overview on what has been proposed for Prague-Electra hard fork. So after Cancun DNAP, I will see some of the proposals. Of course, not all of these will be implemented. The question is what to prioritize, but it's good to have an idea of what might be included. Next, we have this article from Tony from the Ethereum Foundation, Nero, and he studied, basically is providing nice data and visualizations, as usual, it's good stuff, on the effect of increasing gas limits on block sizes and scalability in general. You know, there is this discussion on potentially increasing gas limits on Ethereum mainnet, so it's good to know what are the consequences. There are many consequences, so here we are looking at potential increase in bandwidth requirements as the worst case for the maximum block size will definitely necessarily increase. So we'll see exactly how and how much, why and how much. Then we discuss about slashing mechanics for supermajority clients. You heard for sure about the discussion like what will happen if there is a critical bug in a supermajority client that we get. And you know, this is potentially massive slashing. For me, the question is, I mean, what I want to talk about is why exactly it would create this massive slashing event, and yeah, how does it work exactly? I think it's good to know. Okay, let's start with the proposals from Prague-Electra, and I will add the link to the sources because there is this nice summary and visualization from Team Baiko, and the summary also in the forum with the list of all the references. You can find information on all of these. And let's start. So again, it's not like all of these ones will be included, but it's good to know what might be included. Probably not even 50% of what I've shown before will be included. The question is what is more important or more urgent to be implemented in Prague-Electra that might arrive by the end of this year. So we start with this EIP, execution layer triggerable exits, and this, I guess, is one of the most likely to be implemented. So what is this? Here, the goal is to allow validator exits to be triggered directly from the execution layer, even if you control only the withdrawal credentials. So normally, or at least today, you need to control the validator key, the signing keys, the active keys to initiate the validator exit, that is to stop staking. After this EIP, you can trigger this exit and basically stop staking directly from the execution layer with your withdrawal credentials. This is particularly useful if you think about liquid staking protocols, how to make them more trustless or more trust minimized. It's good to have this EIP. Because today, to exit, you need to trust the operator to actually exit. Like the operator controlling the signing keys has to trigger the exit. While here, you can withdraw, you can trigger the exit, even if you own just or control only the withdrawal credentials. So there is that. Then we have Verkle trees. This is big. Yeah, I don't know if it will be implemented already with Prague-Electra, but anyway, it's something that will come for sure at some point, because we need to change the way we store state in, so the data structure for state. Currently we use Merkle Patricia trees, and the idea is to start using Verkle trees. Why Verkle trees? Because then it becomes much easier to have cheaper light clients. So you need lower requirements for light clients. And in general, it's needed to achieve statelessness. So what is this property? What is a stateless Ethereum? It's an Ethereum in which nodes will not need to store state to verify blocks. So if you want to verify blocks, you don't need to store all the state. That's amazing. You know, it becomes much lower requirements to verify. And why would that be the case? Because in a stateless Ethereum, blocks will come with full witnesses. And this is only possible, or anyway, it's much easier with Verkle trees. because the size of the witness with Verkle trees will be much smaller, then you can put it directly in the block. And basically, when you download the block, you have everything to verify it, even if you don't store the state yourself. So that's amazing. That's the stateless Ethereum, and that's what is needed for cheaper light clients. Next, supply validator deposits on chain. So this basically what this means is that you don't rely on the consensus layer to track and approve deposits for staking, but everything is done on the execution layer. And in particular, this will be done by appending validator deposits to the execution layer block structure. So the execution layer blocks contain the information to track who has deposited how much ETH in the staking contract. In this way, this has advantages in terms of security, faster inclusion of the staking deposit, and reduction of design and engineering complexity of consensus layer clients, because now they have to track these, but it's easier to do it on the execution layer. Then increase the max effective balance. This, it's a very, very nice proposal. I like it a lot because there is this thing that bothers me of the 32 ETH, that the max effective balance today is 32 ETH. And this is only because of some original design. So the initial execution sharding design required to have this constant 32 ETH for all validators that you need to stake. And the minimum is also the maximum. You have 32 ETH for everyone. And this is not needed anymore. But we pay the consequences for this. Because now we have so many validators, even though we have 1 million validators and 10,000 nodes, something like that. So that's of course inefficient. Too many validators, too many messages, too much stress on the peer-to-peer network. So this has to go. As one way or another, we want to reduce the number of validators. There are just too many and really for no reason on this. So the idea is to increase the max effective balance, allow validators to have more than 32 ETH as balance. Of course, there are more considerations like what do you do with the slashing penalties? How do you incentivize people to actually do this kind of consolidation? So consolidation, what does it mean? That if you are a big staking entity and you have many validators, but you're just one entity, now you have these thousands of validators, but you might want to consolidate them when the max effective balance has increased. And this has some advantages for sure, like reduced complexity in handling keys. And we can discuss more about that. But for sure, for solo stakers, the incentives are very clear. So especially, small solo stakers, let's say you have one validator. If you have one validator, you don't care about consolidation. You're not reducing the number of validators, but the incentives for you are very clear because you will have automatically a compounding effect because you will not be swept. Your balance will keep increasing and auto compounding. And also you have better capital efficiency because let's say you have 40 ETH or 48 ETH. I mean, you have more than 32 and less than 64. You don't have enough now to have two validators, but in this way you can have just as much as you want, more granular. So yeah, this is nice. Let's see if it will be included. Next, precompile for BLS12-381 curve operations. So here the point is that there is this curve and this cryptographic primitive that is being used, but there is no precompile. It's being used because there is demand from rollups, for instance. And it would be much better, much more efficient to have a precompile here. So this proposal is there since some years. I read that there were some concerns about the implementation, but now everything should be clear and safe. The benefit in the end is to provide a precompile for a curve for which there is demand, and in this way we'll have more efficient operations, operation for BLS signature verifications and snaps verifications. So nice. Let's see if it will be implemented. Next, inclusion list. This is also very interesting. As you know, the question here is about censorship resistance. So we like Ethereum to be as censorship resistant as possible. And well, Ethereum has the advantage of having a long tail of solo stakers. So these solo stakers that care about neutrality and the censorship resistance of Ethereum, normally we might rely on them to include all kinds of transactions. So don't. But the problem, or anyway, what happens is that to earn from MEV, you basically delegate block building to builders, well, searchers and builders. And yeah, you need to do that to avoid losing all this income or yield from MEV. But now, if you do that, then you delegate block building to some other entities, and you cannot contribute anymore to the censorship resistance of Ethereum, or at least not actively. You have to trust builders. And builders, you know, normally they care about returns, first of all. So the idea here is to propose, to introduce a mechanism in which block proposers, like even if they delegate block building to builders, block proposers will still be able to specify a set of transactions that must be included for subsequent blocks to be considered valid. Then proposer slot n, I'm not specifying the transactions that must be included in this block, but in a future block. And that would be the only way for that would be one of the criteria for this block to be considered valid. That's what inclusion lists provide. This way, the proposers will still be able to contribute to censorship resistance without losing MEV. Next, EIP for forwards. So this is quite big change. So the idea would be to remove the requirements to serve historical data. So clients can locally prune historical data. Full nodes can prune historical data. What we mean by historical data, anything older than 1 year. And this is a change that can be done because to validate blocks and propose blocks, you don't need to know the history. There are clear advantages here because we reduced the storage requirement by hundreds of gigabytes. You know, today to run a full node, to be decently comfortable, you need 2 terabytes. So, and this historical data is growing, it can only grow. So the idea here is to prune this, to allow people to prune the data and reduce the storage requirement. This will also reduce bandwidth usage, and there will be no need to maintain code dealing with historical state. So there are definitely advantages here, but of course then we will very explicitly need to rely on archival nodes. And I think the last proposal I'm bringing today is the EVM Object Format, or EOF. The idea here is to go from an unstructured contract data or code data for the EVM in something more structured, where you have a version, a section for the code, a section for the data. And the main benefit of this is that, to provide a structured format for the code. And that is very important because today there is no such a structure. So basically the code has to be validated every time you run the contract, at runtime, every time. And that takes time. It's clearly inefficient. If you have a version, if we have EOF, then the code will be validated only once at deploy time. So that's definitely an improvement in the efficiency of the EVM, reducing the execution overhead. So yeah, that's the benefit. And right, that was the last one indeed. So let's move on. Block sizes, gas limits, and scalability. And I will link, of course, the article from Tony. Let's have a look at the main plots. So first, introduction, we need to look at the gas usage over time. So this is a history of Ethereum with different hard forks, and we can see that gas usage has increased over time. Indeed, we increased gas limits over time, and the question is, should we increase again? Should we allow larger block size or a larger gas limit. It's not exactly the same thing, of course, because gas limit is about computational complexity, how many complex transactions you can include in a block, and then the block size is the actual size of the block in bytes. So yeah, this is a measurement of the gas used, and this is a zoom on the timeline after London, so after EIP 1559, and basically how do gas limits work today? You have a 50 million gas target and a 30 million gas limit, meaning that in a block you try to have, the EIP 1559 is structured in a way to incentivize this equilibrium of 50 million gas. If more than 50 million is needed, then the gas cost will increase, otherwise it will decrease. So you have this kind of feedback to go back to the equilibrium of 50 million gas per block. But there is a hard cap, there is this limit. So if you talk about the limit, today is 30 million. And that's the max. You cannot put more than 30 million gas in a block. So I really like this plot because actually I didn't know that, how close we are to a target. So yeah, the feedback really works. This gas used per day, and basically you can have variations from block to block, but at the end of the day it averages very close to the target. So yeah, it actually works. And it's always nice to see how well things work. And then there are plots on then what happens if we increase the gas limit. So we allow people, or anyway block builders, to put more transactions in a block. So today we have 30 million as gas limit, as I said, and this plot is about what is the maximum block size in function of the block gas limit. Today, the worst case, like the largest block size that you can have after compression, is 1.7 megabyte, and you can see how it increases linearly with the block gas limit. So that's important to know, because if we decide to increase the gas limit, then this will have an effect on bandwidth utilization. So that's hardware requirements at the end of the day. And when we say we want anyone to run a node, this anyone sometimes is not very clear. Like really anyone? No, there are some hardware requirements, and we need to have informed decisions. So we need to know how the bandwidth requirements will change with increased gas limit, among other things. And the other potential impact on the max block size, so again bandwidth requirements, comes from cold data gas cost. Because let's say we keep the gas limit at 30 million, and so we have this and we have this gas cost of 16 gas for cold data. The block size, the maximum block size, will be 1.7 megabyte. So yeah, this point, this 1.7 megabyte. Now, if we change the gas cost for cold data, like we decrease it, then we can put more cold data, of course, because the same operation costs less gas. So in practice, you can put more of that data, and this will have a very high effect on very strong effect on the block size. So it's also good to know. Now, what will happen with EIP 4844? It's not about changing the cost for cold data, but about allowing blobs. So we have blobs for data posted by rollups, so for data publication. What will be the effect of EIP 4844 on the average block size this time? So the average block size, and you can see it here with time, this block size, and this is the beacon block, so this is what we have today. The average block size is 125 kilobyte. Now, EIP 4844, for current specification, we have a target of 3 blocks and a limit of 3 blobs and a limit of 6 blobs. So again, it works like EIP 59, and you have this target, and the cost to publish blobs will change depending on the demand. So the target is 3 blobs. So let's say on average you have 3 blobs, and each blob is 125 kilobyte. So the average block size, including the blobs, will be 4 times the current block size. So yeah, average block size 500 kilobyte after EIP 4844. And then we also have the worst case. This increased from 1.7 megabyte to 2.5 megabyte. And this is with 6 blobs. There is the blob limit. Next, and the final topic for today, slashing mechanics for supermajority clients. So we know there is this risk about massive slashing event in case of a critical bug in a supermajority client. We know we have a supermajority client that is get for the execution layer. The question here is how exactly this slashing happens, why, what can be done, what cannot be done. So I think it's nice to look at how exactly these consensus rules and slashing rules work. I will add a link to the article from Dankred that goes through this in more detail. It's very nice, highly recommended to read. But let's look at some basic things here. And I will start from the beginning, like what is justification and finalization. These are the basics we need to know. Here I'm putting epochs. These are not blocks, and this is the first epoch. This is the second epoch. So what is justification and finalization? To finalize the chain, you need to justify an epoch first, and then justify the following epoch to finalize the current epoch. But yeah, let's go step by step. This is the genesis, this is the first epoch. And the first thing to do, you need 66% of the stake agreeing on voting on this supermajority link. So we have a link from the first epoch to the second epoch. The first is justified by default, and the second then will be justified thanks to the supermajority link here. We have the 66% of the stake in agreement that we have to vote from this source to this target. Next, you have another epoch, and you start voting from this source to this target. And if you have this other supermajority link, again 66% of the stake, this epoch will become justified, and this epoch goes from justified to finalized. And after something is finalized, you know that basically it's impossible to revert it unless 66% of the stake is slashed. So at least 66%. So this is what will happen. After you finalize, you cannot go back. This is the concept of crypto economic security, because to change this history here, then you will need to have all those resources and have them burned. So since the next epoch, this must be consecutive epoch, is justified, then this epoch becomes finalized. This is how justification and finalization works. Now, let's go ahead and show the problem. Now, we have this epoch that is justified and finalized. This epoch number 2, let's say it's just justified, and at this point, there is a bug, a critical bug in a supermajority client. And this bug, supermajority means more than 66%. And this client now suddenly will justify an epoch with an invalid block. So this is not a very likely bug, of course, but it can happen that the client will not only produce an invalid block, but also believe that the invalid block is valid. So everyone running this supermajority client will actually validate the block, attest to it, and start creating this supermajority link. And this link will actually work because this is a supermajority client. So these people are more than 66% at stake. So suddenly you have this supermajority link, meaning that this epoch containing an invalid block becomes justified, and the previous epoch becomes finalized in the view of these supermajority client stakers. If this problem is not detected immediately, like in less than an epoch. So we're talking about 12 minutes. Then there is another link, another supermajority link. You have this other epoch, and now this epoch that was justified becomes finalized. And that's the problem. Like, this is the disaster. This is what should not happen. Because at this point, everyone running this supermajority client will have this epoch finalized. Now, what happens to the rest of the of the network? Because we talked only about people who are running that supermajority client. In parallel, there is a minority of the stake, so less than 33%, that is running other clients. And let's say that on those other clients, you don't have the same bug, which is, of course, extremely unlikely that you would have the same bug if you run an independent software. So on the other side, these other people, for the first one, these first two epochs that we have here, they're the same. But then, while the other part of the network with the faulty client was finalizing the epoch 2, justifying epoch 3, the rest of the network couldn't finalize, but they go on. They go on with their version, with their fork. And these links I put here, they're dashed because they're not supermajority. You cannot justify, you cannot finalize anything because you don't have 66% of the stake. So there is, at this point, you cannot finalize here on the good fork. And the only way to finalize would be to create a supermajority link on the good fork. But you don't have 66% of the stake. So you cannot finalize. So the only way to finalize at this point is either you let the stakers that were running the majority client lose all the stake, because from the point of view of this fork, the rest of the stake is offline. So they will start losing stake to quadratic inactivity leak. This gets bad very fast. Or if this stake wants to join the good fork, they're forced to do something like this. So you see, 3B and 4B, let's say at this point, the rest of the stake wants to get in the good fork, and they can do that by, for instance, patching the old client, or start using the minority, any of the minority clients. So they can join the new fork, but to do that, you see, the majority link that we have to create must start from the last justified epoch, and this will be the number 2. It's the same for both. And we have to use as target these 5, but the problem here is that suddenly all of these people are slashable, because you can prove that there was a surround vote. So there is this vote from this source to this target, but at the same time, there is also record of this vote from 3A to 4A for the bad stake. This is a surround vote, and this is a slashable event. It's one of the few things that you really cannot do. Double vote, surround vote. And yeah, this will be massive slashing event, and basically the only way is to get to just wait until you this part of the stake becomes the 66%, because in this fork, then if you wait long enough, the other stakers will be slashed, they will go below 33%, and finally this good fork can be finalized. But yeah, so this is how it actually works. Or at least for me, it's easy to see this way, with thinking about what this part of the network sees and what this other part of the network sees. And yeah, I hope you find it useful. And yeah, I want to clarify, this is nothing new. There was more discussion these days because of some events, some bugs in minority clients. But this is a risk that we need to be aware of. We were already aware of. And the question is what to do, of course. But yeah, that's all. And yeah, thank you for listening. And I will come back for another update in 1 week, 2 weeks from now. Let's see. And thanks again. And until next time, ciao.